Let's do a deeper dive into cyclic groups. If I have any group and I pick an element and I start to look at all of the powers of that element, assuming multiplicative notation, since I don't know anything about commutative versus abelian versus not in this group. I get this set, a to a power. That is a subgroup of G. We proved that last time. I'm going to call it the cyclic subgroup generated by A. And we use this angle bracket A notation for this. If any of our elements generate the entire group, then the group is cyclic. But even if the group itself isn't cyclic, we can still look at these subgroups within it. Within the Klein 4 group, we had EA, EB, and EC. Those were generated respectively by A, B, and C. None of them generated the entire Klein 4 group, but those are still cyclic subgroups within it. Now, depending on our choice of group, this subgroup may or may not be finite. If it is, then the order of the element is the size of that subgroup. Otherwise, the order of my element is infinite. What I would like to try and do today is to try and find a way to describe every cyclic group and all of their subgroups. This looks like a hell of a thing to set out to do. Got less than an hour and a half. We're going to be, no, this is actually easier than you might think. But to do that, I need to establish some relatively direct and I think fairly easy to establish facts about cyclic groups. If I claim it, write it as a theorem, something other than a definition or something we've already shown, I need to be able to prove it. So how do I go about constructing a proof that a cyclic group must be abelian? I think I can actually do this one directly instead of by contradiction. While I could try and set up a proof by contradiction, then I would have to show that a universal statement is true, right? I think it's actually easier to just go after that direct universal statement. What's the definition of being abelian? What? The operation's commutative, right? So let's show that if I do G1, G2, you get the same thing as if I do G2, G1. Now, since my goal is to show that a cyclic group is abelian, I now need to look at what's the cyclic mean. Further up the page. A group is cyclic, got a generator. Let's call that generator A. I can use A to build the entire group. To tell me about G1.
I mean, like G1 is equal to A, then the operation on A again.
But I don't know if it only happens twice, right? Mm-hmm. But it's got to happen eventually because I build all the powers of A this way, right? That's what this is. So eventually, as I do all these powers, somewhere along the line, I hit G1. And somewhere else along the line, I have to hit G2. I don't know where. I don't know when. I do know that there are two integers, R and S, where I can build G1 and G2 out of those elements. A to some power R, it might be A squared, it might be A to the 37th, it might be A to the negative 5th, I don't know. But it's A to some integer power. Same thing with G2. Now let's go through the calculation for abelian. What's G1, G2? What's G2, G1? Are they the same? How do you know, Ian?
Well, I mean, I haven't written it down, but A to the R times A to the S.
Which would be G1, G2.
Right, is equivalent to G2 times G1, which is A to the S times AR.
Well, how do I get there from here, right? What you're telling me to do is switch these. But switching those is the thing I want to prove.
Okay.
So I can't just directly claim that. There's got to be an intermediary step.
That'd be like a to the r plus s.
And those are integers. What do I know about addition in integers?
Another integer.
I get another integer, but also
Yeah,
addition in integers is commutative, right? So I know that this is the same as s plus r. And Ian, that gives rise, by doing the law of exponents again, ASAR, which is G2, G1. Okay, look at that. G1, G2 is equal to G2, G1. And I picked those two elements at random within my group. And that means they could be any elements in my group. That's a universal proof. Pick any two, and you switch the order, and you get the same thing. And Colin, I could do it directly rather than doing it by contradiction. Yes, sir.
So so we don't. What are so it's not a big deal that we didn't like get super definitive with G1 and G2 at first, I guess.
Yeah, the whole point was that I wanted to show this would be true for any possible two of them.
Gotcha.
So let's just pick two at random and then name them. Fred and George. Tom, Dick, and Harry. When we do associative, right, I need A, B, and C. Why A, B, and C? Well, who cares? There just have to be three things. Well, this helps me because it means I never have to worry about whether or not I'm dealing with an abelian group. If I know it's cyclic, it's automatically abelian. It's automatically abelian, I should change the way I write them.
Is it just because that would be useful since having a group be abelian is useful?
Yes, but that doesn't tell me why I should change the way I write things. Although we did have a statement we made about writing things that are abelian versus writing things that aren't abelian. What was that convention? I promise I didn't hallucinate this comment into existence. We made a comment deliberately about the way we write groups. And I said, when my group is abelian, I'm going to write it this way. And when my group is not abelian, I'm going to write it a different way. What were those two ways?
As a sum or a product.
Aha! I said that products would be ideally for things where I didn't know. And sums would be for things where I knew it was abelian. And this means that from now on, if I know a group is cyclic, I'm going to write it with addition rather than multiplication. This is not required, but there's a reason to do this. And that reason comes from the integers. Because as we showed previously, the integers themselves are an infinite cyclic group. You get 1, right? I get 0. And then if I keep adding 1 and 1 and 1 and 1 and 1, I get all the rest of the integers that are positive. I take their inverses, I get all the integers that are negative. By the definition of the group, the integers are abelian under addition, work perfectly. And they're cyclic. But I can even go further. We did this, chapter 4 in discrete. If you have a positive number, sorry, that should be m, and then you have any integer n, you can divide n by m. What do you get when you do that division? In integers. (20 divided by 3). I want integer answers.
I feel like the floor function would have over n.
That would give me one of the numbers, but I get 2 numbers. We gave that a name, the floor of m over n. What did we call it? Sorry, the floor of n over m. 20 divided by 3. Do the division, take the floor. What do you get? Y'all own calculators. You don't have to try and divide in your head if this is stressing you first thing in the morning.
Like 6.2?
I get 6, right? 20 over 3 is 6. But there's more. What did we call them?
Remainders.
And
Modulus.
that was m. Quotients. There exists unique Q and R so that n can be written as quotient times the divisor plus the remainder. The remainder has to be less than, not less than or equal to, strictly less than m. Now, as I just said, (20 divided by 3), I have a quotient of 6 and a remainder of 2. What if I did negative 20? What's quotient remainder for negative 20? Divided by 3.
-7 and remainder of 1.
Aha. It's not negative 7, negative 6, negative 2, because that remainder must be positive or 0. We have to go past negative 20. So my quotient is negative 7. And my remainder, positive 1. Because negative 7 times 3 is equal to negative 21. And then I add something to get back to where I want. Got to go down when I do the division. So Why should I give a Because I'm going to use that quotient remainder to prove this.
Well, that makes sense, doesn't it?
I hope so, but how do I prove it? Because
every remainder is going to go up to a certain number before it also resets, right?
Not necessarily. But you're on the right idea. Again, I'm going to do this from the definitions. Proof. Suppose G is cyclic, then G is the generated by A. I don't know what A is, doesn't matter. Pick a subgroup. There are two choices. You either picked the trivial subgroup or a non-trivial subgroup. What's the trivial subgroup again?
0.
Or in our case, because I don't have any particular format, it would be E, right? 1. H is just E. Is that cyclic? Yeah, because you just use E. You add 0 to 0 to 0 to 0, you never go anywhere, right? So let's suppose that we have things other than the identity in there. Well, that means there's some G in here that's not the identity. What do I know about this element? The looks on your faces, the answer appears to be not very much. What did we know about G1 and G2 back in our previous proof?
That it's A to some power.
It's A to some power. I don't know what power, but it's A to some power. I can go a step further. There's also got to be other elements involved here, right? If G is in this group, then its inverse is in this group. Yes? One of those two has a positive power. Either G has a positive power, or G has a negative power, so its inverse has a positive power, right? One of the two of them has to be positive. So without loss of generality, I'm going to assume it's this one. There are lots of other elements. that could be in this group, right? I could do G times G times G plus G plus G plus G, right? Over and over and over. There's got to be a smallest positive integer here. And infimum. Told you we were going to make those classes go together somehow. Any set of integers has to have a smallest non-negative number in it. If it contains any non-negative numbers. If it contains a non-negative number, there's the smallest one. Let m be the smallest positive integer so that a to the m is an element of the subgroup H. Ian, now kind of. If that's the smallest possible positive number, I claim that every other a to the whatever that appears in this H has to be a multiple of that. That's my generator. Good. How the hell do I prove that? With division. B is also a to some power, right? I don't know if that power is positive or negative, but it doesn't matter. Here's what I want you to do. I want you to divide P by M. What do you get? I haven't the foggiest fucking idea. But I know I get a quotient and a remainder, right? Column Q and R, let's write that down. So far, so good. That means that B, which is a to the P, is a to the QM plus R, which is the same as a to the QM, a to the R. Q and M are integers, which means I can multiply them in either order. And if I'm multiplying in a power, rules for powers, how do I simplify that? Or how do I complicate that because I'm not simplifying? How else can I write that?
The power to the power.
It is because I'm multiplying. But I'm going to reverse them. Instead of Q on the inside and M on the outside, I'm going to put M on the inside and Q on the outside. Please note, this is something in H raised to a power. So this whole piece is definitely in H. Way over here, this whole piece is also definitely in H by our assumption. If this thing is in the subgroup, it's got an inverse. Yes? Put it on the other side. Therefore, B times, I want to put it on the other side, A to the M to the Q inverse B equals A to the R. It was on the left, so I multiplied by the inverse on the left. I know, we know it's abelian, it doesn't matter. I'm being pedantic for the moment. What do I know about everything on the left side of that equal sign? It's all in H. And that means that A to the R is in H. What do you know about R I didn't write down already?
Thank you.
More. Not necessarily less than Q, but it's less than something. It's less than M. It's less than the thing we divided. Okay. And it's bigger than or equal to 0, right? With what is written on the screen right now, tell me why I can conclude R must be 0.
Because we said earlier that A to the M is the generator.
Almost.
We know that R and M are both integers in the set, but M is the smallest possible integer, so therefore R has to be 0 then also, right?
The only positive integer smaller than M that's allowed? M was smallest. This can't be positive. And then the only number that's allowed that's left is 0. Hey, wait a minute. If R equals 0, I go back up here. B is equal to A to the MQ plus R, but you just told me that R was 0, and that means that B is A to the M to the something. It's generated by A to the M. And that means that all of H is inside the set generated by A to the M, and A to the M is inside the set H, and the only way to have that two is for those two to be equal. This means that every possible subgroup of a cyclic group itself has a generator. Think back to the example we did of our clock. We looked at all sorts of different options in Z and Zn. Z is cyclic. By the way, it's also generated by -1. That just makes all the negatives first, and then you take their inverses, and that's the positive stuff. Pick a number that's not 1 or -1 that's in the integers. The smallest possible positive integer you can make out of 2's is 2. Look at all the multiples of 2. I don't care what integer you pick. The multiples of that integer form a subgroup. And not just any subgroup, a cyclic subgroup. And if I look at the integers, these are the only possible subgroups of the integers. Hang on a second. If I have an infinite abelian group, it behaves like the integers. I now know all the possible subgroups of any infinite abelian cyclic sum. They're abelian, cyclic, infinite. They look like this. The integers are my canonical example here. What if my group's not infinite? Or what if I want to find the generator and I know something else about the structure of the group? Let's consider a subgroup of the integers. Instead of just giving you one number, I'm going to give you 2. And I want you to take all the multiples of the first one, R, and all the multiples of the second one, S, and I want you to add them together willy-nilly, however you want. This is a giant collection of integers. I claim this is a subgroup. If it's a subgroup, then it's going to have a generator. First of all, I claimed it was a subgroup. How would I prove it's a subgroup?
Would it be by saying like everything that's in the subgroup is in the bigger group, but not everything that's in the group? Or
That would show me that there are things that are not in this set that are in the integers. But what do I need to know that this is a subgroup? 3 things I need to know. Well, it all boils down to basically one thing.
You need to know if it's closed.
You need to know if it's closed. If I take 2 of those things and I add them together, do I get another thing that looks like this? M1R plus N1S plus M2R plus M2S. Rearrange and you get M1 plus M2R plus N1 plus N2S. And isn't that of the same form as this thing? Closed. Technically, I should do things like show that the identity is in there. I should do things like show that inverses are in there. What's the identity in the integers? Really, people? That should be a giant chorus at this point. 0. How do I get something in here that looks like 0? I pick 0 for M and 0 for N. How do I get the inverse of something in here?
Negatives.
Switch the M and the N to their negatives. Poof. Yay, it's a subgroup. If it's a subgroup, it's got to have a generator. Every subgroup of the integers must be cyclic. It's got to have a generator. How do I find it? I promise you, you've done this before. You just don't know that I'm going to apply it here. If I have something that is the greatest common divisor of R and S, then eventually a multiple of that will give me R. And some other multiple will give me S, which means this is something times D plus something times D, which makes it a multiple of D, doesn't it? Once I know what that greatest common divisor is, everything can be pulled from it. Y'all remember greatest common divisors from discrete? Kind of, maybe, sort of. There were methods to find greatest common divisors. What's the greatest common divisor of 42 and 72?
You take 72, divide by 42, and then like find the quotient remainder, and then divide the quotient by.
So there's 142 and 30 left over. Now what?
So then you do like 42 divided by 30 plus remainder.
130 with 12 left over. Iterate this process. How many 12s with what left over?
2 and 6.
Iterate the process. Please notice this number goes over there. and this number goes over here. What's my last set of quotients and remainders? Why do I know it's the last one? If I try to move this one over, I'm going to be attempting to divide by 0. You can't do that. This is my cue to stop, and that means that this number is the greatest common divisor. There was a name for this method. Anybody remember it? Euclidean algorithm.
You can always stop at 0. Is it possible you have like a odd number, say stop at 1?
No, I have to stop at a 0. I have to end up hitting 0 at some point, regardless of what I start with. So, I mean, here's a nice short one. The greatest common divisor of 12 and 25. 25 is 2 12s with 1 left over, right? 12 is something 1s with something left over. Oh, it's going to be 12 1s with 0 left over. Stop. Okay, wait a minute. My greatest common divisor was 1. There was a name for this. You thought you could flush all this crap out of your brains. Nope, I need it all again. 12 and 25 don't share any factors other than 1. Another way to see this is to write 12 and 25 in terms of their prime factors. They have no primes in common. So we call them relatively prime. And by the way, this forces my divisibility behaviors. If the greatest common divisor of R and S is 1 and R divides some product, say SM, well, that means that R must divide M because it can't divide S. Why? Why do I give a damn about this? Now I can prove what I said earlier. Every infinite cyclic group must be the integers. Isomorphic to the integers. And every finite cyclic group turns out to be Zn. Which means if I know what's going on with those clocks, I know everything about cyclic groups. How do I prove that first statement? That if A is infinite, then the order of A is infinite, then G must be isomorphic to the integers. I have to build my isomorphism. What is my isomorphism? Doing it again, just like yesterday. How do I build my isomorphism?
Bijection.
One-to-one and onto function from G to Z. If the order is infinite, then every time I do another power of A, I get something different. I never hit the same thing twice as I generate through the group. Which means for every element of my group, there is a unique power n, so that G is A to the n. I used n up there. Let me use something different. Let's use m. So that means that I'm going to define my isomorphism. Phi from G to Z is defined by phi of G equals phi of A to the m equals m. Since this number is unique for every element of the group, this is a one-to-one function. Since it's from A to whatever power all the way out to infinity, it must be onto. It's got to hit 0 because there's an identity, right? The identity has to go to the identity. We're doing great. Does it preserve the operation? How would I show that? I want to show that multiplication in G becomes adding in the integers. So let's look at phi of multiplication. What happens when you multiply?
You have the powers.
And when I do my isomorphism function, that gives me I plus j. Yes? What's phi of ai plus phi of aj? Oop, j is a superscript, not a subscript. What's phi of ai? What's phi of aj?
Yeah.
But I'm adding those. So whether you multiply first or do the function first and then add, you get the same. We preserve our operation. Phi is an isomorphism. One-to-one, it's onto, and it saves our operation. Now this was set up for the infinite case. Let's look at the finite case. If A is finite, then order of A equals n. Well, what does that mean? It means at some point, pigeonhole principle comes into play. You did this as a homework problem.
Could you explain that one again?
Yes. I start taking a to some power, right?
No, it's pigeonhole.
Yep, I'm gonna get there. A squared, a cubed, a to the fourth. By the way, I also have a to the zero, the identity, right? Eventually, I hit a to the n. But there are only n things, and we included zero. That means a to the n has to repeat something. I have n plus 1 things, a 0 through a n, but I only have n places to put them. Because that's how many spots we have. More pigeons than pigeonholes, somebody gets doubled up. So let's keep going. And I claim that there is some point where we smack back around and we hit the identity again. Well then, a to the n plus 1 must be a again. And a to the n plus 2 must be a squared again. And a to the n plus 3 must be a cubed again. We're wrapping around, right? So then, using the same division algorithm we did before, I get a quotient and remainder, I can show that this is the smallest possible one for any power. I can associate to each element a to the s is a to the quotient and remainder. So what I'm going to do is I'm going to say the map from G to Zn takes a to the s to its remainder. So working here, I would add the powers, right? That would be the same as adding the quotients and the remainders, mod n. And that's why I used addition mod n for the operation here. And it satisfies all of my properties. So if I pick any number you want, and say we have a cyclic group of this order, I know what it looks like. And I'm going to use the example we've been using this whole time. Any cyclic group of order 12 looks like that clock. I don't care what number you pick. You want to do a group of order 7, then it looks like Z7. You want to look at a cyclic group of order 3 that looks like Z3. A cyclic group of order 4 looks like Z4. Another way we know that the Klein 4 group's not cyclic. Any cyclic group of order 4 has to look like Z4. Questions? I now have really covered 95% of my statement from earlier. I know about every cyclic group, whether it's infinite, and therefore is the integers, or finite, and therefore is Zn. I know the subgroups of the infinite one. They look like multiples of some number. What about the subgroups of Zn? What are the subgroups of Z12? Pick a number between 0 and 11. Let's look at subgroups. 10. Okay, let's start adding 10 over and over and over again. Right, Cole? So I want to look at the subgroup generated by 10. Clearly, I'm going to have 0 and I'm going to have 10. I have to have the identity. What's 10 plus 10? Mod 12. Because I'm working in Z12. Divide 20 by 12, give me the remainder.
8.
What's 8 plus 10? 6. Again, I'm adding mod 12. 6 and 10. 16. Mod 12. 10 and 4. 2. 10 and 2. 0. Subgroup generated by 2. If instead of starting with 10, I started with 2 and just said keep adding, what do I get?
4, 6, 8, 10. Do you include 12?
I'm adding a mod 12, so the remainder is 0.
Jump back to 0.
Aha! Hey, wait a minute. That's the same freaking group. And now you can almost hear the plaintiveness in my voice. Why does that happen? What the, man? I promise you this is not coincidence. Let's consider a cyclic group of finite order and then pick something. B in the group, B would be generated by something. It would be generated by here. So B is A to some power. Then the subgroup generated by B, let's call that H, has order of G, which way? That's N. Let's just call it N over D, where D is the greatest common divisor of S and N. What's the greatest common divisor of 10 and 12? 2. 12 divided by 2 is 6. There were 6 things in that subgroup. And there were also 6 things here. Because they had the same greatest common divisor. The greatest common divisor of 10 and 12 is 2. The greatest common divisor of 2 and 12 is 2. Please note this automatically means that all I have to do is find out what numbers have what greatest common divisor. I can get all the subgroups. So I need you to make a list for me. What possible numbers could be greatest common divisors with 12? Well, that's all the possible factors of 12, right? So I have 1, 2, 3, 4, 6, and 12 itself. What numbers are relatively prime to 12? What numbers have greatest common divisor 1 with 12? Well, if you think about it, we really only need to look at the numbers from 0 to 11. Which ones have greatest common divisor 1? But wait, there's more. Well, not in that list.
Yeah.
Greatest common divisor 3 and 12 is 3 divides 12, so greatest common divisor is 3. Greatest common divisor of 12 and 0 is 12. 12 goes into 0, doesn't it? 0 times with 0 left over. 1. 1 itself. Which means the subgroup generated by 1 has 12 things in it. So does the subgroup generated by 5. So does the subgroup generated by 7. So does the subgroup generated by 11. And that means those are all the possible generators of Z12. If you used 11, you'd count backwards around the clock. 11 to 12 to 10 to 9 to 8 to 7. Every time I add 11, I back up 1 hour. If you use 5, we did 7, didn't we? 7, we did that as one of our generated ideas on Thursday. We already did 2 and 10. The greatest common divisor of S and 12 is 2, implies S is 2 or 10. What about the greatest common divisor of S and 12 being 3? Well, then S could be 3. What else could it be? I think it might be to our benefit to mark them off once we've got them. 1, 5, 7, 11, 2, and 10. Got 3. What unchecked thing also has the greatest common divisor of 3? 9. Okay. What's left are 0, 4, 6, and 8. Greatest common divisor of S and 12 equals 4. Well, then S is 4 or 8. Greatest common divisor of S and 12 being 6 gives me just 6. And the greatest common divisor of S and 12 being 12 just gives me 0. Now here's the best part. That's all the possible subgroups. Of Z12. All of them. 2, by the way, is the same as the one generated by 10. The one generated by 3 is the same as the one generated by 9. The one generated by 4 is the same as the one generated by 8. And I can go further. I can tell you how many things are in each of these. How many things are in this one? We already wrote that one out, 6. But if my greatest common divisor is 3, how many things live in the subgroup generated by 3? 4 of them, 12 over 3. As a matter of fact, we even know what they are. 0, 3, 6, and 9. How many things live in the subgroup generated by 4? 3 of them. 12 divided by 4. 0, 4, and 8. Subgroup generated by 6. We only have 2 things in it. 12 divided by 6. Subgroup generated by 0 is just 0. 12 over 12. One thing. But now I can go a step further. I know what these subgroups are. I can make a diagram, just like we did before, with Z12 at the top, and I can look at what's contained in that. The next smallest thing would be this thing of size 6. What about the thing of size 3? Well, it's not contained in the thing of size 2, is it? 3 is not in here. So that's going to be over on this side. Remember, we're doing this hierarchy by containment. But the subgroup of size 4, all of those elements are in here. Sorry, the subgroup generated by 4. And the subgroup generated by 6 is in both of these. And both of those contain the subgroup generated by 0. All I have to do is look at divisors and prime factorizations, and I get everything you could possibly want to know about all the possible subgroups in my group. We did it. If you know that your group is cyclic, you know everything about its structure, whether it's infinite or finite, you know about all the possible subgroups inside. By the way, you'll notice 1, 2, 3, 4, 6, and the whole thing 12. All of those numbers divide 12. I wonder if that's always true. I wonder its reverse is true. More on that next time. See you all then. Oh, wait. Is that correct? Hang on. Schedule. Because, yes, this is the end of the material for the first exam. What are we doing Thursday? Bingo. There's a review sheet. We'll look at it then. Toodles. Ooh, took us right to the